Have you ever seen an APX 432 running live? Probably not, it's forgotten relic from the early 80s. But right now I am going to show how complex the system was. Hi, I'm Mark, and this video kicks off an entire series about that legendary APX 432. Let's bring that beauty back from the dead. APX 432 is one of the most fascinating and quirky processors Intel ever made. Launched in 1981 as their very first 32-bit CPU, it was a radical micromainframe experiment. A fully object-oriented, capability-based architecture designed around the ADA programming language. Everything in the system is a protected object. No row pointers, no plain registers for user code, just high-level instructions that feel like the operating system and language runtime are baked straight into silicon. It supports transport multiprocessing, hardware-protected domains, and capabilities for security that was decades ahead of their time. But it had some serious drawbacks. Bit-aligned variable length instructions, incredibly complex addressing, poor performance compared to the CPU of that era. Even the 8086 was much faster, and massive power draw from GDP. It was built as two-chip set. One chip was for fetch decode and another one for execution. Intel released multiple revisions to fix bugs and squeeze out a bit more performance. But mine is the very first revision, so it's even less performant. So this was the ultimate what-if CPU. A failed experiment that tried to put an entire operating system inside hardware. And today we are going to make it run anyway. To wake the system up, I built a custom board with 4 main parts: power supply, FPGA that would be address command bus slave, SRAM for the external memory that GDP needs, and level shifters to bridge the 5 volts GDP world with my 3 volts FPGA. Usually I power everything from USB and use the same connector for communication, but the 432 GDP is hungry. My old USB 2 port simply couldn't deliver enough amps, so I switched to a wall plug and added a separate UART interface. But to decrease amount of wires around, I reuse the same pin header for both the SPI flashing signals and the UART. One FT232H adapter can now flash the bitstream and act as a USB to UART bridge. Just small reset script required to switch mode to the UART after flash. And yeah, the APX 432 is famous for its high TDP. I slapped heatsinks on both chips right away, and man, you can actually feel the heat pouring off them. Good decision. As usual, nothing went perfectly. I accidentally burned the voltage regulator during testing. Luckily, I use the same circuit in almost every project, so I just stole the chip from my Intel 8080 SBC. I had 3 sockets for that project. 2 salvaged from an original APX 432/100 board and 1 brand new one. Desoldering damaged one of the old sockets a little, so I used the fresh one. It was heavily oxidized, but I managed to solder it, just barely. And yes, if you are wondering why I'm prying the metal plates into the socket with a screwdriver, that's actually the recommended way. The manual says so. Later I started hearing a high-pitch whine from the 5V regulator. A few days later it died completely, probably because it was trying to convert almost 5V to exactly 5V with a regulator. No big deal, I desoldered it and 4.5V straight from USB after all the drops turns out to be perfectly fine for the 432. To get the CPU running, we only need to handle 3 groups of signals. Clock signal, mine GDP is the 5 MHz version, reset, and the bus signals. Bus protocol is actually pretty straightforward. The processor asserts a PRQ signal when it wants the bus, then it sends 2 16-bit words, double bytes in terms of APX. First word has 2 parts, operation specification and low 8 bits of address. Second word is high 16 bits of address, which gives us a 24-bit address space in total. 16 megabytes, not that bad for early 80s. After that, the bus carries data for up to 5 cycles, so it gives us about 10 bytes in total. But there is a couple of quirks that made it more fun. We have 2 clocks, and the signal sampling occurs on different edges. Another interesting decision is that ICS line changes meaning depending on the cycle. During data phases it tells the CPU whether to insert wait states, we don't need any FPGA and SRAM combo are fast enough, and whether there was a bus error. In other phases it becomes the IPC line for interprocessor messages. In terms of data that we got from the bus, very first byte the processor sends is the specification field. It tells us several things. First one is which address space we are talking to, normal memory or interconnect register. Both are 24-bit spaces. Interconnect registers, as its name states, are used for shared data between different components in the 432 system. And access to them from code is a bit costly. Need to use special instructions to read or write them, so most operations are memory-based. Then we have type of operation, read or write. And there is also read modifier write flag, basically a hardware lock. Any other processor trying to read that address gets stalled until the RMW writes finishes. For length field I already mentioned that bus allowed us to have batched accesses up to 10 bytes. But to be honest, I have no idea what modifiers are for. Processor properly sets them, but I don't know how slave should change its behavior based on that modifiers. Verilog code itself is surprisingly clean. Of course, I still managed to make some stupid mistakes. I used the wrong PCF pinout file at first, and I forgot to drive ICS signal low to say that there is no bus error. Initially I just tied to high because I was not going to issue extra IPC and FPGA is quick enough to avoid memory wait states. When it all was fixed, it just started to work. And I noticed a funny detail. At the start the GDP cancels one of its own requests for no obvious reason. Classic 432 behavior. For easier debugging I added a real-time memory access log that I can read from the PC. Let's look at the very first request the chip makes after reset. During initialization routine, GDP continuously checks interconnect register with address 2 to see if any interprocessor message is queued, either global broadcast or local to that processor. To start up, it needs a local startup APC. Then it reads its own processor ID from interconnect register 0, and here's important point. Memory can be shared between multiple processors, so there is just a single hard-coded address, location of initial object table. The ID is actually an index in the global table that holds the current state of all different processors with references to data in memory specific for concrete processor. And after GDP got the idea, it is trying to perform read from that initial object directory. At that point I knew two things. My bus implementation was correct, and the GDP was alive and doing exactly what the manual said. Huge success. Next step would be to feed it real memory content. For interconnect registers I just hard-coded the values in verilog. The rest should be placed in memory, in a SRAM chip. This is where it gets kinda insane. The APX is object-oriented to the core, and after reset it does not jump to a fixed address to start executing instructions. Instead, it expects a whole hierarchy of objects already in memory. The GDP performs almost 150 bus transactions before it finally executes its very first instruction. And that whole crazy boot journey and how I finally got real code running is going to be in the next video. Stay tuned! If you are lucky enough to own an APX for free to GDP, you can easily replicate everything by using the full schematics, verilog and control software code from my GitHub. I will attach link in description. I have already written and run simple programs on it that's coming in future episodes. I'm also hunting for release 2 and release 3 GDPs. If you have one, please get in touch. Thank you so much for watching. If you enjoyed that deep dive into obscure CPU archaeology, hit like, subscribe and other regular YouTube stuff. And I will see you in the next video. It drops in just a couple of weeks. Bye!